Okay, in the last class we have discussed about the address expansion of the memory. Now we will discuss about the data expansion of the memory. Data expansion of memory. Suppose you will be given 32 by 4 or 32 by 2 memories are available. If you want to construct 32 by 8 memory. Here I am fixing this number of address lines, whereas only I want to expand the data. After that I will discuss about both expansions. Okay. Here 32 by 2. 32 by 2 means we will be having 2 bit data bus and 5 bits address bus. 32 is nothing but 2 raised to the power of 5. So 5 address lines. A4 to A0. This is 32 by 2. And 2 data lines D1 to D0. Of course, there is a chip select and read write bar will be there. This will be having some chip select signal. Normally chip select will be active low, as I have told, and read bar write bar depends upon whether the memory is read only memory or read write memory. Now if I take 32 by 8, the only difference is the number of address lines remains same. 32 by 8. This also will have 5 bit address lines, A4 to A0, and data will be 8 bit, D7 to D0. This also will be having some chip select signal. Now basically here this 8 by 2 is the number of 32 by 2 memory is required to construct 32 by 8, because this 32 is constant. This we have 8, we have 2, we require the 8. So the number of 32 by 2 memory is required will be simply 8 by 2, which is equal to 4. Then how to construct this? For that you take 4 32 by 2 memories. Simply connect all the chip selects together. All the 4 memories will be selected simultaneously. So this is having same number of address lines, 5 address lines, A4 to A0. You connect to A4 to A0 of all the remaining memories. You have to connect together. This is 32 by 2, this is 32 by 2, this is 32 by 2, this is 32 by 2. This is overall chip select signal of the required 32 by 8 memory. So here in this will give 2 bits of the data. D0 to D1, or you can call as D1 to D0, MSB and LSB. First you have to represent MSB and then LSB. This will give D3 to D2, this will give D5 to D4, this will give D7 to D6. Total overall this will be 8-bit data bus, D7 to D0. This is how we can expand the data lines. Now how to expand both address and data lines. Okay. Now this overall this will act as 32 by 8 memory. Address and data expansion. Suppose you are given 8 by 2 memory. Required is say some 32 by 8 memory. Now we have this is 8 and this is 32, address also you have to expand, and this is 2, this is 8, data also you have to expand. Okay, you have to expand both. First let us consider only this address expansion, as I have discussed in the earlier class. So in order to expand the address, you have to take the decoder. So how many such? First you construct 32 by 2. First you construct 32 by 2. Later I can easily expand this to 32 by 8. Okay. To construct this 32 by 2 memory, so as we have told that we require 4 such 8 by 2 memories. This is one 8 by 2 memory. This is number 2. You can call this as number 1, number 2, number 3, number 4. So each one will be having, because 8 is the number of locations, 2 raised to the power of 3 is 8. So 3 bits of the address bus. A2 to A0, you have to connect to A2 to A0 of all the address lines. And data lines will be, this will give 2, this will give 2, this will give 2, and so on. This will be having 2 bits of the data line. You can give otherwise at the bottom. This will give 2 bits of the data line. This will give 2 bits of the data line. This will give 2 bits of the data line. This will give 2 bits of the data line. Each one will be having individual chip select signals. We can represent chip select bar, so we can have a bubble here. Now how to select chip selects of these signals? As you have discussed in this earlier class, you have to use 2 to 4 decoder. So, here this 32 by 8 will be having 5 address lines. Here we have 3 address lines. The remaining 2 address lines we have to use as a inputs for the decoder. Two to 4 decoder. A4, A3, this Y0 bar. I am using active low as I have told, Y1 bar, Y2 bar, Y3 bar. So, in the earlier class we have also discussed about this, that for the first 8 combinations this A4, A3 will be 0, 0. For the next 0, 1, next 1, 0, next 1, 1. So, Y0 bar has to be connected to the chip select of the first 8 by 2 memory. Similarly, Y1 has to be connected to the next one. Y2 has to be connected to the next, and Y3 to last. So, in this way we can select 32 locations. The first one will give 8, second one will give 8, third one will give 8, fourth one will give 8. So, all together is 32 locations. But because this is 8 by 2, each memory will give only 2 bits of the data. Okay. This will give 2 bits of the data. We can call as D0 to D1 or D1 to D0. This will give 2 bits D1 to D0. This will give D1 to D0. This will give D1 to D0. But I want 8 bits of the data. So, you have to connect 4 such chips together. As I have told, this is data expansion. So, you have to use 4 such chips. The only thing is chip select of all these 4 parallel chips has to be connected together. This is another 8 by 2 memory, another 8 by 2 memory. You have to connect A2 to A0 of all these memories together. Only chip select is different and data is different. And this will give 2 bits of the information, D3 to D2, and this will give D5 to D4. This will give D7 to D6. Similarly, here also you have to connect 4 such chips whose chip selects has to be connected together. Here also will be having 4 whose chip selects has to be connected together. Here also 4. So, totally we need 16 such 8 by 2 memories to get 32 by 8. So, normally this type of questions will be asked in some competitive exams. So, to construct 32 by 8, how many 8 by 2 memories are required? So, the answer is 16. Eight by 2 memory. So, you have to simply connect this chip select to here also. You take this chip select, connect together all. Similarly, here also all the chip selects you have to connect together. Here also you have to connect all the chip selects together. Whereas address lines of all the A2 to A0 of all the 16 8x2 memories will be common. Similarly, read bar, write bars also will be common. This is about both address and data expansion. Okay. So we need a decoder wherever the address expansion is required, decoder type of the thing, and whenever you require the data expansion, similarly just you have to just connect all the chip selects together, you have to connect in parallel. Okay. So with this memory concept, we will go to the memory interfacing to 8086. Memory interfacing to 8086. As I have discussed in the earlier classes, while discussing about this pins of 8086, there is one signal called BHE signal, BHE bar, which is called bus high enable. So because 8086 is a 16-bit microprocessor, we can access 16-bit of the data simultaneously. But if I take the memory location, each memory location is capable of storing only 8 bit of the information. So the total maximum memory of 8086 is 1 megabyte. Starting with 0000 0h to all f's, FF, FFH. This is the maximum memory. Okay. But each location is capable of storing only 8 bits of information. Then the question is how to access 16 bit of the data. So if I want to access from the 2 consecutive locations, it will take 2 clock cycles. But in 1 clock cycle, if I want to access 16 bit of the data, because there are many operations where 16 bit data is required. So in that case, in order to get the 16 bit of the data in single clock cycle, we have to divide the memory into banks. Okay. We have to divide this into this 1 megabyte into 2 halves. Okay. So 1 megabyte is nothing but 1024 kilobytes. Okay. So half of this one will be 512 kilobytes each. So we will be having memory banks. This is even bank or odd bank, 512 kilobytes. We can call this one as even bank. This is 512 kilobytes odd bank. So all the even address will be present here. The first address itself is even address 00000, okay, and then the next address will be 00002, 00004, and so on. So what will be last address? FFH will be odd address. One above this one is FFEH is even address. So this will be having 512 kilobytes of even address, and this will be having 512 kilobytes of odd address. What is the first order address? 00001H. Then the next one is 00003H, 00005H, and so on. The last one will be FF, FH. Now we know that for even addresses A0 is 0. If I take A19 to A0, A19, A18, so on up to A1, A0, for all even addresses, this A0 is equal to 0 for even address, and this is equal to 1 for odd address. So, in order to select this even bank, we are going to connect this even bank chip select bar to A0. This is chip select bar of even bank, because this is active low signal. Whenever A0 is equal to 0, then only even bank has to be selected. Okay, this has to be connected to A0. Similarly, chip select bar of odd bank has to be connected to this bus high enable BHE bar. Okay, whenever BHE bar is 0, then the odd bank will be selected. Whenever A0 is 0, the even bank will be selected. Okay. Now, based on this A0 and BHE bar, we have 4 different operations. So, if I form a table here, A0 BHE bar, if it is 0 0, what does it mean? Both even bank and odd bank will be selected. What type of data transfer will take place? Data transfer will be word. Word transfer. Either this can be read or write operation. Okay. Both the banks will be selected. This will give 8 bit, this will give 8 bit, total 16 bit a word. If this is 0 1, A0 is 0 means this is even bank, BHE bar is 1 means bus high enable is not enabled, which is disabled. So, this will be only 1 byte from even bank. So, the even bank will give the data bits as, this is even bank, will give these data bits D7 to D0, and odd bank will give data as D15 to D8. Okay. This will be D7 to D0. The byte will be available on the data lines D7 to D0. If A0 is 0, BHE bar is 1. If A0 is 1, BHE bar is 0, then also 1 byte, but 1 byte from odd bank. Means data lanes are D15 to D8. If both are 1s, okay, no transfer occurs, no data transfer will takes place, because both will be disabled. Okay, there will be no data transfer. Okay. So, based on this, we can connect the memory to the microprocessor. I will give an example. Interface, eight kilobytes of EPROM and 8 kilobytes of RAM to 8086. Okay, this is an example. we have EPROM and ROM. So, we have discussed about this ROM, which is read only memory, but what is EPROM is ROM. There are different types of the ROMs, which is called PROM, programmable read only memory. This P stands for programmable. So, at the time of manufacturing itself, the manufacturer will store the data which we cannot change. Okay. So, in case of erasable programmable read only memory, EPROM means here it is not possible to erase the data, whereas here this E stands for erasable programmable read only memory. How to erase the data? We have two techniques to erase the data. We can use either ultravioletically erasable or electrically erasable. So, ultravioletically means if I take this memory IC, the ROM, you can see in your laboratory also. On electrically erasable ROM, you can find a small quartz window at the center of this IC. Here is a quartz window. If I expose this window to the ultraviolet rays with some definite wavelength for a particular time, then the contents will be erased. But the drawback of this type of ultravioletically erasable programmable read only memory is, suppose if I have some 4 locations, each location is capable of storing 2 bits of 4 bits of information, 10 11 11 11 00000001, say these are the 4 addresses, 0001 1011 are the addresses. Suppose if I want to erase only this bit, I want to erase only single bit, that is not possible. In case of ultravioletically, the entire data will be erased. Okay, that is the drawback of this one. So, to avoid that, there is another technique called electrically erasable programmable read only memory. This is called electrically EPROM, electrically erasable programmable read only memory. This also can be called as E square PROM. One E stands for electrically, second E stands for erasable programmable read only memory. Here this is possible to erase a single bit or a single location or the entire memory. Here you can program accordingly, depends upon our requirement. So, this is how this E square PROM is one of the popularly used read only memory for many of the applications. So, here I am using this EPROM. This can be by default, it is a E square PROM. Then we have random access memory. So, 8 kilobits of EPROM, 8 kilobits of random access memory. So, the first step here is we have to choose appropriate memory locations. Out of this 1 megabyte of the memory locations, this is the total memory location is 1 megabyte. Starting with 00000H to FFFFH. We can use any portion of this one for EPROM, any portion of this for RAM. Okay. If it is not mentioned in the statement, sometimes, so it will be given in the statement itself that you interface 8 kilobytes of the EPROM from say some F0000H to F1 FFFH. So, in that case you have to connect in that particular place only. If nothing is given, you can choose any of this space for EPROM and some space for RAM. Okay. But the usual practice is, so whenever the microprocessor is reset, then it will point to address FF FF0H. Upon reset, the microprocessor starts at this address. The IP and CS will be so chosen that it will go to this particular address. That is why normally the last portion of the memory you have to use for EPROM. Okay. So here I am using the last 8 kilobytes of this one for EPROM. This is 8 kilobytes. This is for EPROM. So the last address is FFH. What will be the starting address if it is 8 kilobyte? So earlier also I have discussed about this, how to obtain knowing the starting address, how to know the ending address, or knowing the ending address, how to know the starting address. I will review the same thing again. 1 kilobyte is nothing but 1024 bytes. Okay. 1024 is decimal value. What is the hexadecimal equivalent of 1024? 1024, if you want to convert into hexadecimal, we have to divide with 16. Okay. 16. So what will be this quotient and remainder? 1024, 16 5 jar is 18, 16 6 jar 96, then 96, remainder is 6, 64, 4 is the quotient, 64, and remainder will be 0. Okay. Then if I divide again 16, 16 4 jar 64, 0 is the remainder. 16 4 jar 0 is the 16 zeros, 16 zeros, 4 is the remainder. You have to stop here until you get quotient as 0. Then you have to read from bottom to top. So 1024 decimal is equal to 400 hexadecimal. So 1 kilobyte means total it will be 400H. Suppose if I start with 00000H, one less than this will be 003FF H. This will represent 1K, because 0 to 3FFF means total 400. Okay, because you are including 0. So 0 to 9 is 10 numbers. So starting with 0, if you want 400H, the ending address will be 1 less than this. 1 less than 400 is 3FF, because if I add 1 to 3FF, this will be F plus 1 is 10, F plus 1 is 10, 400. Okay. So if I subtract 1 from 400, it will be 3FFF. So you have to remember that now 00000H to 003FFH is 1 kilobyte. Okay. If I want 2 kilobytes, it will be 1 kilobyte plus 1 kilobyte. Okay. This is only 1 kilobyte. So what is the next address of 003FFH? So you see the ending address starting off another kilobyte will be 1 plus this address. So this will be 00400. Okay. To get 1K, so for 0000H we are adding 3FFF to get the 1K. If the starting address is 00400H, 00400H, for 1K the ending address will be, you have to simply add 003FFH. So this will be FF700. So the ending address will becomes 007FFH. only one F. So this is another 1K. If I start with 00400H, then total from here to here is 1K plus 1K 2K, which is 00000H to 007FFH. This will be 2K. This total, this one will be 2K. Similarly, if I want 4K, this is 2K, 0002 to 007FF is 2K. The next address to this one is 00800H. H. So how to get another 2K? You have to add 7FFF. So 00800 plus 007FF. This will be FFF00. So this two 00FFFH will be another 2K. If I start with 0080H, this is another 2K. So if I start with 00000H and if I end with 00FFFH, then this will be this 2K, this 2K, this is 4K. Simply adding FFF will give 4K. If I want 8K, so what is the next address? Another 4K, 01000H. If I add 1 to this 00FFFH to get the next address, F plus 1 is 10, F plus 1 is 10, F plus 1 is 10. So this will be 01000H. And to get the ending address for the 4K, you have to simply add FFF. If I add FFF here, this will be 01FFFH. So ending address will be 01FFFH. This is another 4K. If I start with 00000H and if ending address is 1FFFH, then this is total 8K. So like that we can extend. Okay. So this is for starting off 0000H, ending is 003FFF, this is 1K. Okay. Here I am going to summarize 1K, 2K, 4K, 8K up to 8K. So normally you will use maximum of 8K, or you can go for even higher also in a similar manner. So 00000H2, 003FFF, H will be 1 kilobyte, and I will start with all zeros only. 000H2, for 2K it will be 007FFH. This will be 2K, and if I start with same 00000H and if I end with for 4K, this will be 00FFFH. This will be 4K, and starting with 00000H, ending with 01FFFH will be 8K. Similarly, if I want 16K, this will be next address will be 02000 plus 1FFF, 01FFFH. This will be 03FFFH. This will be 00000H2, 03FFFH will be 16K, and 32K will be, the next one is 04000 to, we have to add 03FFF. This will be 07 FFF. So 00000H2 07FFFH, and 64 kilobytes we know 4 Fs, starting with 00000H to 0FFFFH. This is the table which will give 1K, 2K, 4K, 8K, 16K, 32K, 64 kilobytes, starting with 00000H. Okay. So with this data, so if I come back to that interfacing of 8 kilobytes of EPROM, 8 kilobytes of RAM, random access memory. So if I want to choose this as a last address, space of this one, FFFH, the last portion of the memory, this 1 megabyte of the memory, the last 8 kilobits I want to use for EPROM. This is 8 kilobytes. So if the ending address is FFFFH, so what is the starting address? For 8K it should be 1FFF. You have to add 1FFF. So you have to subtract 1FFF from here. So 1FFF means this will be FE000H. Is it clear? So FE000H, if the starting address, to get the 8K you have to add 01FFFH. So this will be FF10, sorry, EF, this will be F. So 4 Fs, right? Similarly, so the address 1 below this one is, this I want to use for another 8K for RAM, random access memory. Okay. So it will be starting and ending address. Ending address will be FDFFF minus 01FFF will be the starting address. This is ending address. Ending address is 1 less than this, which is FDFFF, and starting address you have to subtract 1FFF. This will be 000CF. So FC000H. So these are the addresses of this RAM and EPROM. Okay. So to interface this RAM and EPROM in these locations, what is the hardware circuitry required and how these connections has to be made? So I will discuss in the next class. Thank you.